I would like to thank you all for making time for this presentation. Hope it is informative and useful. A little bit about myself. My name is Farshid Hosseini. I got my undergrad and master degree in structural engineering back home in Iran, and then graduated with PhD degree from University of Southern California. My thesis was about next generation seismic resistant structural elements using high performance materials. I have some experience about seismic assessment of tall buildings, and I joined Miyamoto International around 1 year ago. And during this time, I had the opportunity to work in a variety of good projects and get experience under supervision of great engineers here in Miyamoto. So my presentation is about fiber reinforced concrete. And in this presentation, first, I would have a brief introduction about fiber reinforced concrete. Then I will talk about design improvement of a case study we recently completed here in LA office, and about its nonlinear time history analyzing of that building, or suggestions about enhancing the performance of the structure in MCE level, and finally the conclusion. So concrete is the second most consumed product on Earth after water. We used it, we are using it, and we are going to use it in future. I don't think there is anything to replace concrete in near future. But concrete is not perfect. The reinforced concrete structures can damage during cyclic loads, as you can see in these pictures, as well as in corrosive environment. Why? Because concrete cracks, it has a brittle failure mode, and it is pulse. So you may say, what about code? Code provides the minimum requirements to save the life of residents and never guarantees a safe structure. So the code-based design structure may experience a severe damage during an earthquake, and you may need to demolish that after that. The whole purpose of the code is saving the life of the residents. So most probably you're familiar with this graph. So as mentioned, code only provides the minimum requirements, and there are a lot of uncertainty in the code. Using high performance materials, and fiber reinforced concrete is categorized in this range, you can reduce the uncertainty, but to improve it and have a better structure, you need dampers and base isolators, but certainly they need higher investment. So fibers can help. Fiber and using fiber in concrete is not a new concept. Ancient cultures used it in mud bricks to control crack in the concrete. Mud, they didn't have concrete at that time. Okay. And what fibers do? Fibers first control the crack width in the concrete. Okay, it limits the crack width. And if this is a special type of fiber reinforced concrete, and you can see it can generate thousands of cracks, and it's good for permeability of this structure. So if you have less crack with limited width, you improve you enhance the service performance of this structure. Additionally, it holds the structure and concrete together and provides kind of self-confinement effect of the concrete, and prevents spalling in the concrete. Additionally, this one is one of the main characteristics of fibers. It increases shear strength of concrete. Here you can see that by using 1% fiber in the concrete, you can easily double or triple shear strength of concrete, which is huge. Pure concrete without reinforcing. And if you have uh, better shear resistance, and you can provide kind of confinement to the structure, self-confinement. It improves the energy absorption capacity of the building. And the other thing is fiber reinforced concrete improves the bond. Okay, if you have a better bond between concrete and reinforcing, you expand the plastic hinge region. You would have a bigger plastic hinge, so you would have less concentrated damage. You would have higher energy absorption capacity in the structure. So there are different types of fibers. Okay, steel fibers, natural fibers, synthetic fibers, and in each of these categories, you can find like bunch of other different types. Okay, each type has advantages and disadvantages, and based on the project, you can choose what type of fiber you want. So here you can see some examples. The top ones are pure concrete, reinforced concrete, and the bottom ones are with fiber reinforced concrete, the same element. Okay, so on the left side, you can see beam column joint, pure shear behavior. The middle one is a bridge column, flexural dominated behavior. And also on the right-hand side, you can see a beam column joint. I mean, a coupling beam, which is combination of shear and flexure. Okay, for flexural dominate structural elements, fiber reinforced concrete mainly improves the damage tolerance of the element. So you would have higher number of cracks and with limited width. But for shear dominant structures, it changes the failure mode of the element. Okay, because fiber reinforced concrete is more ductile and um, prevents that shear brittle shear failure. Additionally, it increases the shear strength of the system. So having this information, I would like to talk about the case study. Uh, uh, it was an 18-story tower with 3 shear wall cores and also post-tensioned slab. And you can see a little unsymmetric plan and also elevation in the structure. And it was designed based on the code. Our purpose was to respect the code, to design the building in a way that satisfy every requirement of the code, and at the same time add fiber reinforced concrete as a supplement and improve its behavior in MC level, in extreme earthquake event. So the first design, when after talking with the peer reviewer, we figure out that the structure is too stiff. So what stiff structure brings with itself? First of all, it absorbs more energy during an earthquake. And additionally, you would experience much higher acceleration at top. So it amplifies the ground acceleration. So FEMA predicts like hand of rule that, you know, acceleration at top floors amplifies by 3 times compared to the ground motion. So to reduce the stiffness of this structure, we remove the coupling beams and reduce the thickness of the shear walls strategically in different locations to, as I said, satisfy the code requirements about torsion and drift. So by doing that, we removed 61 coupling beams. The contractor got so happy, the owner got so happy. And then we told them that we reduced 1,100 cubic yard use of concrete in the shear walls, and they got happier. So by doing this, I believe we saved around $1 million construction cost by just tuning the building. Okay, so the next step, we performed some nonlinear time history analyzing on this structure using the site specification. This structure is located pretty close to a major fall and around 50 feet, actually. It's pretty close. And site-specified response spectrum shows that we would have around 30% more acceleration compared to the design response spectrum. This is one of those uncertainties I mentioned earlier about uncertainties in the code. Okay, without this investigation, you wouldn't understand and you wouldn't know that you would experience higher acceleration on site. So based on this information, the geotechnical engineer gave us 7 time histories, okay, perpendicular and parallel to the structure. And these time histories need to be applied simultaneously to the structure. So here you can see response of the building to one of those time histories. We defined plastic hinges only in the a nonlinearity basically in the walls and kept the other components elastic. As you can see, the structure performs pretty symmetric with not that much of torsion. Okay, it just swings back and forth, but not that much of torsion, which is a good sign. And those colored circles shows location of the plastic hinges. Here you can see how plastic hinges form in the walls. Most of the plastic hinges are concentrated in the lower 3 floors, and after the 6th floor, where we have a spandrel. Okay, so after spandrel, that giant spandrel, the stiffness changes. Okay, we could eliminate that one too, and I asked the architect to give me 3 inches more for the west wall, so I can increase its thickness to 3 inches more. They disagreed, so we had no choice than leaving that spandrel. Looking to this slide, green means good, not that bad. Okay, blue is the next, and red is the worst. Okay, as you can see, most of the red dots are in the bottom 3 floors and also in the wing shear walls. Those are very important for us in this building because they were controlling the torsion of the structure. So in addition to location of the plastic hinges, we also measured the drift and also acceleration in all 7 time histories and averaged them for both MCE level and DBE level design to be sure that they are in the limits. Okay, as you can see here, for DBE level, they're in the limit of 2%. And for acceleration, you can see that the acceleration didn't amplify that much, okay? Because the structure was soft, the amplification in higher floors amplified around 1.5 times. For comparison, for like in Wilshire Tower in Los Angeles, and the amplification, the acceleration amplified around 2.5 to 3 times in the higher floors. And also we measured the strains in the concrete and reinforcing steel. This is one of the examples. We did that for all the shear walls and in the height, and also for all 7 time histories, and then we averaged them. We wanted to see where we passed the limit. The limit for concrete is 1%. Okay, and this is one of the cases that in MCE level, the strain passes 1%, but in DBE level, we are fine as it was based on the code. But we want to improve the performance of this structure for extreme event, which is MCE level. So we identified the location of the concrete that basically you have a major damage, like crushing and spalling. But and we adjust amount of the reinforcement in the shear walls to have strains less than 5%, which is the limit for MCE level. To have a better understanding what those red and green dot means, in the walls with colored by red, we expect some behavior like this. Okay, spalling, crushing in concrete, followed by buckling of the reinforcement, and huge cracks in the bottom and mainly in the boundary elements. And the green ones, definitely the reinforcing fails, yields, you would have cracks, but not that major cracks. They would be like normal crack along the wall. So we have the location of the damage and we know what happens to the shear wall. So, and we know that concrete crushes, okay? But we don't wanna invest too much and use dampers or isolators. So fibers are one of those that by minor improvement, you can get higher return. So we specified steel fiber reinforced concrete, okay? Um, Based on the literature and also our investigation about the performance of the structural elements with different dosage of the fibers, we specify 100 to 130 pound per cubic yard concrete. These steel fibers are directly added to the concrete on site and can be pumped. That's one of the major concerns of the contractor, and can control the cracking in the shear walls and enhance the concrete deformability, and at the same time increase concrete shear strength. So here you can see how 170 pound and 130 pound fiber per cubic yard looks like. It is flowable, workable, it's pumpable, and uh, and you see that there's a high density of reinforcement there, so it's constructible. So having this information, we didn't want to specify the same amount of fiber in everywhere, okay? Because we wanted to specify higher dosage to places experience higher damage. So having this information, for example, these are the wing walls that were important for us, and we specified higher dosage of the fibers for first 3 floors and lower dosage of fiber for upper floors. And you may say, okay, how much it costs? Okay, fiber itself is not expensive. For whole building, we calculated that it is around $1.2 per pound. And we calculated that for whole building, the fiber cost would be around $230,000. And it can, but you should, but it uh, reduces the slump a little bit. You need to add some high range water reducer to the concrete, and you need more effort for pouring that. But fiber itself is not expensive. And with low amount of fiber, you can reach high performance in this structure. Okay, so what we can conclude from this project that In general, fibers control the crack widths, prevents concrete spalling, improves the confinement in the concrete and the structural elements, and um, more importantly, increases the shear capacity of the walls. And we can improve the deformability of the structural elements and their ductility by using fiber reinforced concrete. And also, we can have better plastic hinges and with better performance and improve the seismic energy absorption capacity of the structure. And in general, improve the resiliency of the structure with lower uh, investment. Okay, that was my presentation. Hope, thank you. And I'm open to your questions. If yes.
You're really talking about, a different material, really,
Yes.
when you're talking about the fiber reinforced concrete. So I'm wondering how you were able to demonstrate to the peer reviewer what the material properties were for the fiber.
Okay.
For the fiber with for the concrete with the fiber in.
Okay, thanks for the question. Ken's question is about how we can demonstrate the structural properties of the fiber reinforced concrete for peer review, right?
Yeah.
So it has been done a lot of research, and you can find a lot of literature about fiber reinforced concrete, especially for steel fibers. It is also accepted by code, and right now, by specifying 100 pound per cubic yard steel fibers, you can eliminate the minimum shear reinforcing. So it is already accepted by the code, but for minimum uh, replacing of the shear reinforcement. But the point is here, we are not replacing anything, okay? We are designing everything based on the code, and we are assuming that the fibers are not there at this stage, okay? We need more research, we need more experience for later on, but at this stage, we assumed first fibers are not there, okay? Then we design everything and add the fibers as a supplement to the fiber. We know it improves the behavior of the structure, but we don't rely on that much on that in DBA level, in design level. In our case, okay, every time we wanted to prove something, okay, we were finding like some literature review, some tests, okay. For example, I found some uh, results for coupling beams, okay, and we were trying to follow the same mix, the same fibers, and basically whatever they used. So we had some documents to prove that this mix at least works.
If you needed to try to prove with the peer review, if you were trying to use it to actually replace like diagonal reinforcing a couple of things, are there like curves for like the nonlinear modeling of concrete with fibers that you could use? Or they're like, is that available in the documentation?
Yeah, thanks. That's a good question. Danny's question is about, do we have any documentation about the curves and plastic hinge for behavior of the fiber reinforced concrete, for example, in coupling beams? Uh, that in the code? No. So we don't have anything in code right now except for the replacing of the minimum shear reinforcement. Okay, so that's the reason we stick to the code and assume it's not there. Okay, if we wanted to improve the, for example, rotation capacity of the coupling beam, again, we were referring to 3-4 experiments So we were saying that these are the experiments with this uh, reinforcing uh, shape, okay, dosage, and with this type of fibers, and all of them showed, like, for example, 100% higher rotation. Okay, so we go with lower bond, we add 50% more rotation. So by this approach, we could convince the peer reviewer, like mainly by experimental works done by others.
I got a question. So this, how's the like adding the fiber gonna affect the concrete performance under like severe conditions like fire?
Fire? Oh, that's a great question. Uh, Andy says, what is the performance of the fiber reinforced concrete in fire? Okay, so what happens to concrete during fire? Okay, it is paused. Why? Concrete by nature has around 100% more water than what it needs for hydration. Okay, and we call it free water. It's inside the concrete. So when you expose the concrete to fire, though that water uh, turns to steam, puts pressure to the concrete, and concrete starts falling and is falling. Okay, so that's the tricky part, that the type of fiber change the behavior of the fiber reinforced concrete. If you have steel fibers, they improve the conductivity of the uh, concrete. So it actually makes the situation worse. Okay, because heat can transfer deeper in the concrete. But when you have synthetic fibers, okay, during fire, they burn, okay, and leave some small voids inside the concrete, okay, so that steam has a place to run and reduces the spalling amount in the concrete. That's the strategy that uses for offshore structures, and also in the tunnel that connects France to England. Okay, they use synthetic fiber there as a strategy to control fire. Synthetic fibers to control fire, because it actually controls fire spalling in the concrete. And I heard that they are using that strategy in oil industry too. Any other questions?
Hi, Farshid. This is John in San Diego. Do you put any? How do you model it in ETABS? Do you do something different?
Uh, in ETABS, so his question is about modeling fiber reinforced concrete in ETABS. So fiber reinforced concrete, what happens? We used fiber hinges there. Okay, fiber hinges behavior is dominated by behavior of the material. So to change the behavior of the steel is there. We didn't change the steel that much. But for concrete, you can increase the, because when you have fiber in the concrete, it increases the crushing strain, and also it changes the behavior of the concrete in tensile. And you can change those behavior in ETABS, okay, by defining material nonlinear behavior. But in this project, again, we didn't rely on that, okay? We said concrete is not there, okay? Concrete is not, I mean, fibers are not there. So we defined everything. I basically based on the normal concrete, and then our decision was at the end based on the damage we saw uh, in the during the time history analyzing. But it's possible. It's you can change the nonlinear behavior of the material in tabs. You need to give higher because it gives kind of self-confinement to the concrete. You can increase the compressive strengths and also post post-peak behavior in behavior of the concrete by assigning higher strengths, and also you can change the behavior of the concrete in tension. And in case of coupling beams, when you are assigning, for example, uh, rotational capacity with concentrated plastic modeling approach, you just increase the rotational capacity of the coupling beam. And you can choose better hysteresis model.
Hi, this is Lon in Sacramento. Can you hear me?
Hey.
Hi there. Hey, couple questions. So you showed us what the fiber cost in and of itself. Did that include any additional labor or additional costs in conveying the concrete due to the steel fibers?
Okay, that's a good question. And the question is about the slide I showed about fiber costs include other costs like labor or superplus. I mentioned that that cost is only for fiber itself, $1.2 per pound. But you need to add cost of superplasticizer. Okay, the pumping rate might be lower, and you may need to have the device for a longer time. You may need to vibrate the concrete more. Okay, those increases the cost of the using fiber reinforced concrete. The slide I showed is just for steel fiber itself, not other costs.
Okay, thank you.
Thank you.
This is so you did a nonlinear dynamic analysis then, right?
Right.
This is just out of curiosity. How long does it take to run your model under nonlinear time history?
Okay. The question is about the time each nonlinear time history analysis took, and it depends. In general, it depends on how good the uh, computers. Okay, how much RAM you have, and also how many data points you want. Okay, so if you specify that during time history analyzing, you need to save the all the results every 0.2 seconds. Okay, it's like thousands of data points. Okay, and if you reduce that number, the computer would skip those steps, and it would be faster. The other element that causes like the duration of the analyzing is the amount of nonlinearity you see uh, in the structure. For example, when you have uh, like dump plasticity, when you specify plasticity in a specific point and you define that curve, okay? The moment you pass the limit, and if you pass that, basically it has A, B, D level. The moment that one of those elements passes the limit you defined, analyzing gets super slow. Okay, so since I had the structure was very close to the fault. The earthquake and time histories were strong, and I saw some severe nonlinearity in this structure. It was taking around 20 to 24 hours for each one of those time histories. And since I was applying like 2 of them perpendicularly. So yeah, usually, but as I said, the main reason I had that long analyzing duration was because I wanted to save higher number of points. If you reduce it like to 100 data points, okay, you definitely would have like much shorter period, which is around like 6 hours. Okay, but when you are trying to find the maximum, find the maximum strain in the specific point, okay, the structure goes only to that 100 points and finds the maximum in that 100 points. And most probably you skip the critical point with having that large saving time. Yeah, it can range for normal computer can range between 6 to 24 hours. That's the rough number. Any other questions?
Hi, this is Tom at Sacramento.
Sacramento, yeah.
Okay. And I have just one quick question because the analysis was done by like normal concrete properties, but in the field, the fiber reinforced concrete will be used for this like specific lower floors. And in that case, are there any possible negative factors to affect for the analysis? Because, for example, I'm not the specialist for this fiber reinforced concrete. So if, for example, the modulus of elasticity will be changed by using the fiber reinforced concrete, I just simply guessing the period of the buildings will be changed because the stiffness will be changed by using this fiber reinforced concrete. So for example, are there any potential negative factors by using this one? Because analysis was done by normal concrete.
Okay, thanks for your question. The question is about, like, since we analyze the structure with normal concrete behavior and adding fiber reinforced concrete may affect the elasticity of the concrete. And if we later on add use fiber reinforced concrete, is or analyzing is valid or not? Okay, so we defined it can happen for normal concrete too. So you design a structure. For example, when we were designing the analyzing the structure, we were careful with those parameters too, because the aggregate in LA is not good. Okay, and the modulus of elasticity of the concrete here is different than what code specifies. Basically, it's lower. Yeah, but did we use it exactly there? No. Regarding the fiber reinforced concrete, it doesn't change the modulus of elasticity of a structure, a concrete that much. Okay, because you have the same mix there. Okay, we don't change amount of water, cement, aggregate, nothing. And it just changes, like, it may have effect, but it's not that major. And the main effect is for like the post-peak behavior. And and improves the post-peak behavior of this structure. And since we designed this structure in dBE level based on elastic analyzing, I don't think that that argument is valid here, and it won't. And using fiber reinforcing would affect our analyzing and the results we had from the analyzing.
Okay, thank you.
Thanks. Thanks for the question. I think if.
Thanks, Farshid.
Thank you. Oh. Oh, 5. Hope it was useful, and please let me know if you had any other question later on. You have my email. Just shoot me an email. I would like to answer the questions. Thank you. Thank you for your time.